There's 6, process synchronization, as you can see. What that means basically is once you have an operating system with many processes, they may come into conflict. So you need to synchronize them. Synchronizing means making the processes work without interfering with each other. These are the subjects we'll talk about: critical section problem, Peterson solution, synchronization hardware, etc. Okay, background. Reset. Process can execute concurrently. They may be interrupted. If they're running concurrently, they may access a shared memory, and this can cause inconsistencies. Because if I'm writing and you're writing, then the data will get ruined. Because I might write an A, I might write the word hello, and you might try to write the goodbye, and I'll get an H in, and you'll get an O in, and you'll get gibberish.
It is only applied to threads.
Threads or processes. This is whenever you have multiple processes or threads, you can have. You're right. You're saying processes don't normally have the shared data, so processes have less of this problem, but they also can have this problem because if you want them to, you can actually assign them shared space. In other words, by default, put it that way. By default, threads have shared space, but processes don't. But you can change that. You can create shared space between processes. And then once you create that shared space, then you can create problems.
And we're assuming that they have those cross-reference cross-access.
That was hardware. That was with the
Are we assuming that all our processors have that, or
doesn't matter. Okay. Here I have an example. Suppose that we wanted to provide a solution to the consumer-producer problem that we already talked about that fills all the buffers, which we saw. We can do so by having an integer counter that keeps track of the number of full buffers. Initially, the counter is set to 0, or it's incremented by the producer after it produces a new buffer, is decremented by the consumer after it consumes the buffer. So one is incrementing, one is decrementing the same shared variable, but that can get screwed up because I think I have an example. We'll see a little bit better, but it can get screwed up because the process of changing the number is not one atomic action. It's not an action that can't be divided. It can be divided. What does that mean? We talked about context switching between processes. When you context switch from one process to another, let's say we're doing round robin and the time slice finished. So we go to another process. So now he will start doing stuff. Question is, when will the processor stop me? The processor will never stop me in the middle of a single hardware instruction. If I've done half of the hardware instruction, I'm going to get to do it all. It's not going to stop me in the middle of a hardware instruction. Between 2 different hardware instructions, it could interrupt me. So a single hardware instruction, by definition, is what's called atomic, which means it's uninterruptible. It can't stop me in the middle of doing it. But other actions, like an incrementation of a counter, C++, actually could be more than one operation, because there could be the register that has the value, but then there's also a variable called counter, in other words, in the memory that I'm changing. When the compiler turns your program up, when it says you write, let's say I++, the compiler does not turn it into one line of code. It turns it into several lines of code, because he's got to keep track of the I, and he's got to keep track of the incrementation. The incrementation is going to happen in registers. But there's also a variable I, which is going to be in memory, which he has to copy it to. So the I++ action is actually several actions. And therefore, if it gets interrupted in the middle, 2 people can increment the same variable, and it can get incremented only once, but it should get incremented twice. I think I have an example of that in the slides in the continuation here. But before we do that, let's look at the producer. That's just in general the idea. Producer, consumer. So, did we see this before? Is this the same as we saw before? Produce an item in the next loop. So while counter equals buffer size, do nothing. So what is this loop going to do? If we didn't give you okay, here's the example, but fine. Whatever. Here is our we discussed this example before, and the point is not to understand this example right now. The point is just to see that this example, if you remember, was the example of producer consumer where we used the entire buffer. And we did that by introducing a second variable called counter. We do counter ++ here. So the counter ++ is going to check here. Counter is equal to buffer size don't go on. If we don't produce anymore, we're full. So this counter is crucial. And then the consumer also uses the counter. If the counter is empty, there's nothing in the buffer, don't take anything out. So this counter is very crucial. And this decrementation is very crucial. But look at this problem. Counter plus plus and counter minus one could be implemented by these three lines, like I was saying. It could be that take the register, stick it into the variable, then, or sorry, take the variable, stick it into the register, then take the register that you have and add one to it and put it into the register, then copy the register back into the counter, and the same thing by the minus. So as long as these three things are done as long as when let's say producer or consumer is doing his decrement, he gets to do all three of those things, there'll be no problems. This algorithm will work. And so too here, as long as the producer gets to do all three of those things when he does counter plus plus, there'll be no problem. But you could have an execution like this, where let's say count is 5. And then then he takes counter and he puts 5 into register 1. Then he puts 6 into register 1. So 6 is in register 1. But before he copies it back to the counter, the other guy comes and reads counter. Counter hasn't changed. Counter is still 5 in this first yellow line. So he'll copy also 5, and he'll change it to minus 1, 4. And he'll say register 2 is 4. Now we'll come back the first one and it'll say counter equals 6. And then this guy will say counter equals 4. And we'll get 4. But what should we have gotten? We should have gotten 5, because if it was started off at 5 and we did adding and subtracting, it should be what it started at. It should be still 5, but we got 4 because of these switches in the middle. What are these switches? That's when the operating system decides to stop me and start somebody else, and that we call that a context switch. So since this can happen,
What's the context switch you said?
context switch is when in a round robin type algorithm, where after a certain amount of time, we stop one process and let another process get the CPU. So since we can stop one process and let the other process go, and they're using the same data, they have to be using the same data, because the producer-consumer problem only works if the counter is a joint variable, is a shared variable. So we need to make these three actions what's called atomic. We would like these three actions somehow to be done in an uninterruptible fashion, that the operating system can't stop. But okay, that's for the particular case of producer-consumer. But there's a general problem which we call the critical section problem. Consider we have n processes. Each process has a critical segment of code. For example, what are critical sections? Processes may be changing a common variable, updating a table, writing to a file. Why are those critical section problems? Well, common variable means that I'm trying to change it, you're trying to change it. And we can have, just like we saw in the counter example, a corruption of the data. Also, updating a table in a database. If we're both trying to update the same table at the same time, whoever is last will determine its value, but it could be that he read it like just like we had there. One read before, and then the other one read, and then I change it, and you change, and we get the wrong thing. Also, file writing to a file. Like I gave the example of I try to write to a file hello, and you try to write goodbye. Some of the letters I could succeed, and some of you could see. We both start at the beginning, and we start writing letters. Who knows who's overwriting whom? So those are critical section problems. When one process is in a critical section, we want to have a situation that no other process will be in that same critical section. In other words, relating to that same file. Critical section problem is to design a protocol to solve this problem. So we're going to come up with an algorithm to fix this problem. Each process must ask permission to enter the critical section. So I guess this is one way to do it. Or put it this way: in all of our problems, we're going to discuss these three parts. We're going to discuss the entry section, the exit section, and the remainder section. What do we mean? The entry section is when I recognize I'm about to enter into a critical section. I'm about to do something that may have an effect on another process, that may require synchronization. That's the entry section, before I go in. And I wait at that section until I'm allowed to go in. Then I go into the critical section. and then I leave the critical section. So each process must ask permission to enter critical section in the entry section, may follow critical section with an exit. And then the remainder section is whatever he's doing when he's no longer interested in that critical section. He's finished writing or reading that section, and he's now going on to do other things in the program. So here you see a picture of the same thing. You have entry section where I decide, should I go in or shouldn't I go in? Then I do the critical actions, in our case, C++, or counter plus. I exit the section, and then remainder section, other stuff in my program. And then I make a while true loop, which means that I'm going to go back to the top again and try to get the critical section again. So those are the sections. Actually, there are 4 sections that we'll talk about. Now, any solution to the critical section problem has to supply 3 criteria, has to satisfy 3 criteria. One is called mutual exclusion. That's the most obvious idea. That means when I'm in my critical section, nobody else will be in it. So that means if I'm writing to a certain place in data, nobody else will be trying to write there. That's called mutual exclusion. When I go in, I exclude you. When you go in, you exclude me. Second thing is progress. Progress means that those people that are waiting to go into the critical section are those people that decide who goes into the critical section, as opposed to some arbitrary other force or other factor that decides. What is written here? If no process is executing in its critical section, and there exists some process that does want to go into its critical section, then the selection of that process that was in the critical section cannot be postponed indefinitely. Postponed indefinitely means that like it's dependent upon another factor, an external factor. Kind of like if I would want to go into the critical section and a policeman would let me in, but he could be busy. He could be eating donuts in the donut shop, and then I'll never get in because I gotta wait. I can't go in until he lets me in. Donuts. I wish we had American donuts. I like it.
Krispy Kreme?
Well, I'm old fashioned, so I like Dunkin' Donuts. But Krispy Kreme also good. Also is very good. My favorite though is the I don't know if they make it. They used to make crullers. So crullers, they make them.
I don't know. Why not?
A cruller is like a straight donut, and I like the devil's food glazed chocolate crullers.
How about donut
That
holes?
sounds like.
Can we have a donut party at the end of the semester?
Yeah, I'll pay for it if you find a donut, if you get American donuts.
What about donut holes?
American donuts?
My dad goes once a month.
Oh, I'll pay for it if you get me donuts.
Write you down an order.
However many you
I'll
want.
talk to the students, if you send me an order, I'll
Yeah.
have the students send me an order, it should be mental
Okay.
Wagner's first order of business.
All right, my son, who is a tzaddik, went to America for sleepaway camp and he brought me back a dozen donuts.
Really? Did it survive?
They survived, yeah, in his suitcase. What?
What a guy.
Yeah, he actually indulged his father's, idiosyncrasies. So progress is a very strange thing because it's sort of like how are we going to decide who gets to go in? It has to really be those who are involved. The processes that are involved should be the ones to decide, and not some other third process, some other external process. That's the basic idea.
So they all share responsibility. External third process. Was that?
Well, if I'm waiting for some other process to let me in, and that process is not in the critical section and is not interested in the critical section, he has nothing to do with the critical section. Maybe yesterday he was involved, but now he's not involved. And he doesn't relinquish it right away. In other words, when I have left my critical section, I should immediately I should notify everybody, I am no longer going to be an obstacle for you to get in. Because I've gone out, I've left.
Mutually exclusive.
I've left, but now I've left, so it's no more mutually exclusive. Now I'm letting everybody in. If I forget to let everybody know that, then nobody else can get in. Why? Because there's some other process that's not interested in getting in, who is tying up the whole system. So basically what progress means is that whoever has ceased to be interested in using the critical section should notify all the other parties that he has ceased to be interested. Otherwise, they'll be waiting for him and he'll never notify them. So that's another way, that's a positive way of putting progress. Progress means that when I do leave, I notify you that I'm not, don't let me be the obstacle for you getting in.
What if they're the first?
Even if I'm the first. I'm the first one, I go in and then I go out. Now I say,
So you go.
I am no longer in. I have to announce that. If I don't announce that, then the second guy will come and he'll think I'm still there.
So I meant more like, if I'm the first, if I'm going in on the first process, I've not waited for anyone to tell me that's clear.
We don't care. We're talking about the algorithm. We're not talking about a particular instance. We're going to judge an algorithm to see if it satisfies this for a set of processes, not for one.
You also have to announce that you're in.
For sure, that's mutual exclusion. Mutual exclusion says when I go in, I have to tell everybody. Progress means when I go out, I have to tell everybody. That's basically, I mean, that's the most straightforward way of defining it. Bounded waiting. What is bounded waiting? Bounded waiting means that there exists, that a bound must exist on the number of times that other processes are allowed to enter their critical section after processes meet the request to enter its critical section before that request is granted. In other words, if that's a way of a rule that says all red-haired processes get to go into the room first. So black-haired processes may never get in because there may always be a red-haired person at the door. So there's an unbounded wait. A bounded wait would be something like first come, first serve. If I get in other words, because I've been waiting for a while, then I'll eventually get in. In other words, if there's but it's not amount of time, it's amount of processes. If we have a rule, for example, that says black-haired people can get in, but they have to let 10 red-haired people go ahead of them. So that's a bounded wait, because I know after 10, there's a bound to how much I have to wait. After 10, I get in. But if it's unbounded, which is, for example, as long as there's a red-haired person there, then I can't get in. Then I could prefer, for all I know, I'll never get in. So that's also a requirement of critical section. We don't want a solution to the critical section problem that leaves some processes starving outside. It's like starvation. Leave some processes starving outside, never be able to get in. So we're not talking. Assume that each process executes in a non-zero speed. That's another. We always, in all of these assumptions, in this especially in the last one, we assume that a process will not be infinitely in the critical section. Then it would be unbounded wait. Now, when we're talking about a bounded wait, we're assuming that the processes are in their critical section for a finite amount of time, and we can't assume anything about the relative speed of the process. We can't say, oh, he'll probably get in because these ones are fast. These are fast processes. We can't assume that, but we can assume that they're finite. You can't assume that how quick they are. We can assume they're finite. Okay, so those are some ground rules, basically. So here is our first solution. It's called Peterson's solution. It's a good algorithmic description of solving the problem. It's a two-process solution. What that means is that this only works for two processes. It won't work for three. Assume that load and store instructions are atomic. So first of all, we have these two instructions called load and store, which we're about to see them used. And they're atomic, which means they cannot be interrupted. So in other words, there's a single hardware instruction. Any single hardware instruction cannot be interrupted. The two processes share the two variables turn and this two-dimensional array, not two-dimensional, two-variable array called flag. The variable turn indicates whose turn it is to enter the critical section, and the flag array is used to indicate if a process is ready to enter its critical section. Flag of I equals true implies that P of I wants to go in, is ready to go in.
So the size of the array is the amount of processes? Or?
Well, it's only two. In this case, it's only two.
I mean,
No, this is a solution for two.
Solution only.
That last sentence talked about I because I could be either 0 or 1.
Oh.
In this case, I could be either 0 or 1. When we write these solutions, well, we'll see the next solution. So here, so look how nice guy I am. Yeah, in the book, it only writes this once. What I did was I wrote it twice because it's confusing otherwise. Because basically what we're saying is this is the solution. This is the way you'll see the solution in a textbook, in any textbook. And it'll refer to I and J. And you're just like, who's I and who's J? What? So the way you have to think about it is I'm I. Remember, it's a two-process solution. I'm process 0, and J is 1. J is the other process. So I'm I and he's J. But I did it. I just rewrote it again where Where here, I'm the other process now, I'm PJ. Process J, so he's J. So let's read this, I'll translate this program to you into English. So follow along. Flag of I equals true. Flag of I, we said, means I'm interested in going in. So what we're saying here is process I, am interested in entering the critical section. But I say the turn, whose turn is it? It should be your turn. I'm very magnanimous. I am deferring to you. You can go in. I don't want to go in. I would like to go in, but it's your turn. So I'm not going to go in. And the other guy says the same thing. The other guy says, I'm interested in going in. Flag of J equals true. But the turn, oh, it's your turn, my friend. Now, what happens when both of them say that? Somebody will be the last one to say, no, but somebody will, they're not going to say it twice. Whoever said first, it's your turn, end up being his turn, right? Because I say, let's say process I says it's J's turn. And then process J says, well, no, it's your turn. Well, so now it's my turn. Now when I get to the next line, whose turn is it?
Oh, it's yours.
It's my turn. I made it his turn, but he came along and made it my turn again.
Is that a shared variable? Turn?
Yes,
Couldn't it be like?
turn is shared and also flag of I. Flag is shared. We said that. Flag is also shared.
Couldn't it still happen that there's some race condition where what both of them say that it's their other's turn locally? But both of them have stored the variable that's.
No, we're assuming, I mean, did it say it here in the previous part? We should have said that. Load and store. Do we see load and store here? Yeah, oh, this is kind of. I should change the slide. This is the way it's written in the book. Load and store instructions are atomic. What they mean by that is the assignment operations.
Oh. So those are.
Assume the assignment operations are atomic. We're not going to be dividing, we're not going to be, if they would be atomic, if they would be, sorry, dividable, non-atomic, then this would get ruined. This could get ruined.
So make more of a problem, more of a critical.
That wouldn't, yeah, then that would be a critical section problem itself. That would
Oh,
become a
so
critical
it's
section
a
problem. So when we said the load and store are atomic, we mean this is atomic. So let's go through it again. I say I'm interested, but it's your turn. You say, oh no, it's your turn. So I come here, I check like this. Flag. Is the other guy in flag of J, that's him. Is the other guy, because I'm I, is the other guy interested in going in? Oh, yes, he is. But is it his turn also? Is it his turn? No, it's and turn equals J. Wait a second. Sorry. Turn does not equal J because remember I said turn equals J, but he changed it back to I. So even though he's interested, it's my turn. So the fact that it's my turn is going to break this loop and get me, as this semicolon here means that it's an infinite loop until it's broken. So this is, as soon as this is broken, which it will be broken now because both conditions have to be true for it to be keep looping. But as soon as one condition is false, I break through. Which condition here? Turn. It's true that he's interested, but it's my turn. So I'm going to go into the critical section, do whatever I need to do. And then I'll say, and here's the key point, I'll say flag equals false. Now, what does that mean? That means I am no longer interested. And that's where we see the idea of, what is that called? What condition do we meet when we do this? Progress. Because you see, I left and I said, I'm no longer interested. Don't let me be your obstacle. Now, wait a second. Who's the turn? Whose turn is it?
Still J.
It's still I's turn. No, it was I's turn. Because remember, turn was not equal to
We
J.
didn't turn it back.
I didn't turn it back. I just said, I am no longer interested. True? I just said I'm not interested. I didn't change the turn. Did not change the turn. I just said, I just checked. I did my critical section and I said, I am no longer interested. At that moment, this guy is over here. Let's say he's in an infinite loop, waiting forever. Well, he was waiting forever because the turn was actually I. And the flag, well, I was interested because he said he's interested. But the minute he says it's false, he's going to break through and he's going to go into his critical section, even though it's still not his turn. But he'll get in. But that's fine because he said he's not interested. So he got in. And he'll say, I'm not interested. Now they're both not interested. And they go back to the top. And they both say they are interested now again. And you could say, well, wait a second, could happen. They go back to the top again, by the way, and they'll have the same situation again. And now one of them will go in first. So that so far seems good. But wait a second, you could ask a question. No. What if he's in this loop here, but the time slice is very long? And so he made it that he's not interested. And then he did his remainder section. And then he came back here and he said, he's interested. Oh, he's interested again. Ah, but now he says the turn is whose?
It's always changed though. You never switched it back to I.
No, it was I. He turned it to I. That's why he got in. Now he changed it to J. So even if the time slice is very long, he won't keep grabbing it because he'll immediately say it's your turn. So now if this guy finally got the thing, if he finally got the time from the CPU, he'll actually find out in this case that turn is not only his turn. No, turn is not equal to J because it's him. And well, he'll find now the other guy is interested. Now there's the minute the other guy is interested, he'll get stuck. But the minute he gets the J here, he'll get breakthrough.
It says turn equals equal to 5.
What?
I feel like
If it is I, it'll stop. It'll stay in the loop.
I feel like the while.
The while line is its own loop.
If the left side is the I process, right?
Yeah.
Should be while the flag I is true and turn equals I.
No, that would be I'm interested and it's my turn, then don't do anything. Remember, it's not an if. You're thinking the while is an
Oh,
if.
that's yeah.
You're thinking the while is an if. The while is it's like saying it's a while to say the opposite, right? Don't go on unless one of these conditions fails. So it's provable that progress requirement is satisfied and bounded weighted. So that's Peterson's solution. Very nice solution. You have to know. Now,
Peterson's a good guy.
Peterson's a good guy. Wait a second. Yeah. So, in a sense, that previous solution required some kind of minimal hardware support. What did it require hardware support for?
Sure.
Atomic store.
Atomic store of a variable.
Yes.
Now, that had to be an assignment operation, which we called load and store. I don't know why we call it load and store, but is it load?
I
Whatever.
mean, it is like,
Load is usually taken from memory.
it was store for sure. It wasn't.
I don't know why we said, I don't know why the book writes it that way. I would prefer to just say assignment.
Actually, no, it does make, it does make sense, like. When you're copying from the variable, you're just loading into that variable from the shared memory. And when you're storing, it's the same thing, like it is just the load.
I understand, loading and storing is regarding, but what about the registers? In other words, are we saying just the,
It's not.
You're saying all the memory. That's the thing.
Yeah.
But
It's in
the-
the.
okay.
when you do something that's equal to something, you're just
doing load word, that address of the first thing, the address of the second thing.
so why say load and say store?
Because store is when you have to set it. And it's turn, store is
Oh,
when you're setting the array in memory. I think.
Because the other guy's about to change the rest.
Maybe.
wait a second, so what are you saying? You're
Maybe I'm
saying,
wrong. It's-
you're saying that there's a difference between.
I think
Between this one, between equals true and
I
this
think-
one equals turn, no, they're both setting, they're both setting. I don't see a difference.
maybe
between
you're right,
these.
you're right, I don't know.
I don't know, whatever, it doesn't really matter. Just understand the way I said it, that.
Yeah.
When we said load and store, what we meant was the assignment operation.
Yeah.
Okay, so we said that there had to be a certain minimum amount of hardware support for that load and store. But there could be better hardware support for critical section solutions. And we'll have to have the idea, well, they're all based on the idea of locking, fine. Locking means that you lock a variable or you lock a critical section. In other words, you lock something, you lock some kind of variable, you say it's locked and then unlock. You have a lock before you go into the critical section. You have some kind of variable. In our case, it was a flag. Let's say that said it's your turn or it's my turn. The turn variable was a lock. Because I can't get in unless the turn is set to what it should be for me. So that's like a lock. Oh, so if you had just one, how could you achieve, this critical section solution? One idea would be if you had a uniprocessor, in other words, you just had one processor. You could just say disable interrupts, context switches. Just say no context switch, just the operating system could say, I'm not gonna do a context switch for these three instructions. I don't need any special hardware then. I'll just use regular hardware and I'll just, whenever I see that instruction, I won't do a context switch now. Somehow the operating system will just know. But that's not going to work if you have multiple, if you have two processes running on two separate CPUs. Because that means one CPU would see that instruction, you have to lock the other CPU also. You have to shut down all the CPU, in other words,
Oh, we have to control the other.
it would have to control the other one too, and that would be kind of weird.
It's a unit wheel.
Generally, it's too inefficient to do this kind of solution. Why? Well, you don't want to, you want to let the system run as it normally runs. You don't want to stop it from doing context switches. Operating systems using this are not broadly scalable because the message needs to be passed to all the other processors, right? It has multiple processors. You need to somehow notify them, don't do a context switch, or you don't let somebody else, because think about it, I don't let any other process on my chip and change that variable, but if that variable is shared to another chip, and he's also got to not let anybody, then he has to actually, again, just not allow context switch, that other processor would have to stop running, because maybe the process that's currently there is about to change it.
Or in the middle.
Or in the middle of changing it, so he'd have to actually stop the other processors from running. Basically, it's impossible. So modern machines provide special atomic hardware instructions. Atomic, as we've said a couple times already, is non-interruptible. Two examples are set and test and compare and swap. In other words, those are the concepts. So we have some kind of operation called test and set, or so let's go through them. So the idea is like this. First, we're going to just show a general description of what we mean by locks. You acquire some lock, you go to the critical section, you release the lock, let everybody else go to the critical section. You do your remainder section where you don't need the critical section, and you go back. That's the
Locks
basic.
are in hardware.
What? This would be a program. Acquire lock will be something in hardware. The acquire lock will be some kind of hardware. The critical section will be whatever I want to do, and the remainder will be whatever I want to do. But the acquire lock will have to be some kind of atomic action. So here is an atomic action. Now, this confuses the students unless I tell them the following thing. This is not a program or a function. It looks like a function because we have like a return variable. It looks like a function, but it's not a function. It's just a description using the language of functions of a hardware operation. This is a hardware operation. Boolean test and set is a hardware operation. The book writes it like this as though it's a function. It confuses all students. But since I tell you that it confuses you, it doesn't confuse you anymore.
I'll just know that we confused.
Boolean RV. So this is a Boolean variable which gets the value of the target. Right? This is getting a pointer to the target. This is getting dereferencing it, getting the value. Then we say change that value to true. So we set it and return. What is this? The original value. That's the original value. See, first thing we do is we copy the original value into RV, return value, and then we're going to return it. So we're going to return it, whatever you had there before, we're going to give you back, whether it was true or false. But no matter what, we're going to set it to true. So whatever variable you give me, I am going to give you back two pieces of information. First of all, I'm going to tell you the fact that that variable that you sent me is not true. Secondly, I'm going to tell you what it had been before. And that whole thing will be an atomic operation in hardware. Now, that doesn't sound like it solves anything because it doesn't, but it will solve something with the program. So when you want to solve the critical section problem, you've got to use that operation like this. So you say like this, test and set lock. So we said we're going to have a variable called lock, and that's the lock that I'd like to get in. If the lock is false, that means it's not locked. The lock is false. It's not locked. So if it's false, we could go in. So I'm going to test it. Now we're going to return the value that it was. Let's say it was false. It was false. So I should be able to get in. So test and set will return what value?
True.
No, false. The previous value of it. it'll return the previous value of it false, while false will break the loop and we'll go into the critical section. Wonderful. Well, we don't know what it is. I said if it is false, I said if lock was false, then what value will we return by test and set? And the answer is false, because we always return the current value. We do two things. Test and set does two things that I said. One is it returns the previous value, and secondly, it changes the value to true. And does it in in a twinkling of an eye. It can't be interrupted. So test and set on a lock is going to change the lock from false to true. But in the meantime, it returned false, so the loop broke, and I went to a critical section. If some other process is doing the exact same operation right after me, he's going to get that the lock is true and set it to true. So he's not going to change it, but he's going to get true. But true, while true, is going to be a loop. So this loop will go on forever. This will be an infinite loop for him because I went in. And then I go and I say lock equals false, which again is not going to be a problem. Actually, nobody else is trying to change lock. Well, actually, he's trying to change it to true, but no, it's shared. But I'm going to change it to false. But next time he does test and set, he's going to get that false. Again, this is also an atomic operation. This has to be an atomic operation too, just like it was.
No one else is in that section.
No, because at the moment I'm writing false, if he's writing true over here, if this, he's saying if this is atomic, then nobody else can be doing it. You're right. I guess that's enough. If this is atomic, then then he can't be doing this false at the same time. So that's enough. I take it back. This doesn't have to be atomic, but this has to be atomic. So there we go with the test and set. We see a very simple way of keeping people out. And as long as I'm in the remainder section, when I'm not interested, I've released everybody else, so everybody else can go in. This solution works. Yeah, everyone understands? Any questions on the solution? Test and set again returns to me the value that it was. If it was true, then I'll be stuck out here. If it was false, I'll get in, but I'll change it to true and lock everybody else out. Does this solution satisfy our conditions for two processes? Well, it's certainly got mutual exclusion. It's pretty much got progress because while I'm in my remainder section, he's going to come in and do that, presumably. If he's
Doesn't mean that no one else can get it. There is unbounded wait time now.
why?
There's no, it doesn't seem like there's a built-in.
Well, if there's two processes, is there unbounded wait or bounded wait?
No, it's bounded because there are only two processes.
Right.
When one releases the other, we take it.
Right. But if there's three processes, then what could happen is that let's say it's A, B, and C. It could be that A goes in, releases it, B goes in. Then B goes in, releases it, A goes in. And then A releases it, B goes in. And A and B keep releasing it and going in, and C never gets it. Because at the moment that one of them releases it here, it's first come first. It's whoever grabs it first. There's no management of the queue. There's no say there. There's no organization of the line.
Even though C's been in that loop longer than not.
What?
Even though C's been in that loop longer than A after.
Yeah, we're not saying that there's a queue that's managed by first come, first serve. If we would throw onto this a queue, like beforehand, some kind of queue, then obviously it would be bounded wait. If we would keep track, but we have no queue here. We just have everybody jumping at the same time for the same, piece of Barakas. Whoever gets it first gets it. Here are
Parentheses, but too many people try to grab it, nobody gets any.
crumbles. Great example. Now here's the same idea that was test and set. Same idea with another atomic function called compare and swap. And this one, I don't know if it gives us much advantage over the previous one, but it's more complicated. So let's look at it. It's not really so much different. But we have here a value expected and new. It gives us, we're basically going to check is the value equal to our expected value? Maybe there is an advantage. We have to think about what advantage this might have.
Doesn't have to be a Boolean.
It doesn't have to be Boolean, exactly. It doesn't have to be Boolean. What advantage would that give us? But
If you put a queue. You can get 1, 2, 3, 4, and 5, and then each process will only jump in when their number comes up.
then what do they release? When I release it, I only release the one that I took. So nobody else will ever get it. When I let's explain it. Here again, is this a function or is this hardware description? This is a hardware description. It looks like a function, very misleading. Compare and contrast. No, not compare and contrast. Compare and swap. So temp equals value. So first of all, I grab the value that I got and I store the original value. Then I check, is the value equal to the expected value that I was given? Is it equal to true or false, whatever I want to check? Then if it is equal to what I expected it, then here's new value. There should be an underline here. New value will be assigned to the value. So in other words, if this is, let's say, true and this is false, then if I got true, then I'll change it to false. But if this is 3 and this is 4, then if I got it equal to 3, then I'll change it to 4. It's more flexible. And then I return temp. What's temp? The original value. So let's see this a working case. Here's a working case. Here we just did it with Booleans. I don't know if there's any advantage to doing it with, I mean, it would have to be like, again, you do with 0 and 7, but I don't know what the difference is.
Why can't you use this to have a couple of programs in a row, processes in a row? You put this lock instead of setting it to 0, you put it, or if you're 1, you set it to 2, and then the one that's checking for a different compare and swap would be checking for 2, and the new value
saying-
would be 3.
Say 0, 1, and the next thing goes 1, 2.
Yeah, and then you
Maybe.
just pass it on to the next one.
Write it out, and see if it works.
Too scary.
No, not on a computer, but on paper. Work it out.
Oh.
Work it out. Don't be too scared. You can't,
I thought you meant make the computer start doing that.
even if you would do it. First of all, you couldn't make hardware, but you could try to simulate
It's
hardware.
not a program.
Right. But you could do it on paper. You could work it out. Don't do it now. At home.
Homework, all right. I'll write down next one.
Write down as at homework. Okay, compare and swap. So here we're using it and we're setting it with 0 and 1 and lock. Lock again is some kind of Boolean, shared Boolean lock initialized to false or 0. So we check, is our lock equal to 0? That's what we're checking. We're checking, is our lock equal to 0? Compare. If it is, then set it to 1. That's what that means. So if it is false, we'll go in. If it's not false, if it's 1, then we won't do anything. And we'll return 1, that it's locked. And if we check that it's not equal to 0. Why do we check this not equal to 0? Well, right, 1 is not equal to 0, so it keeps looping. Fine. This is redundant, not equal to 0, right? You could have just written, you know that in C++, if you just put a number here, you don't have to write that it's not equal to 0. Anything that's not equal to 0 is going to be true. And then we release it here with lock equals 0. Same basic idea. Remainder section again is some kind of code. Doesn't have to be long. It could be 0 lines. But
What is compare and swap return?
compare and swap returns the value of lock. See, we return temp. Temp was the value of lock, of the first parameter. Lock. So if lock was false, this is going to return 0. 0 is not equal to 0. Basic. It's going to return 10, which is value. So if it was false, this is going to return 0. And we're checking, is 0 not equal to 0? No, it's not. So it's going to break out of the loop. A little bit double negative, a little bit confusing to think about. 0 is equal to 0. So therefore it won't do the loop and it'll go into the critical section. That's if lock was 0. But if lock was 1, it'll return 1, and 1 is not equal to 0, so it'll stay in the loop. So if it was locked, it won't go in. If it was unlocked, it will go in. And what's the 0 and 1 for? Well, that's just what I check over here. Where do I check? Here. In other words, here's a 0 and 1. If it's equal to 0, then don't leave it as 0, change it to 1. If it's equal to 0, which means it's free, it's open, then lock the door. If the door is open, which means the value is equal to 0, then lock it. Change it. But if it wasn't what I thought it was, then don't lock. Anyway, you can think about what advantages this other one has, if any. Okay, now we have another example, bounded weighting, mutual exclusion. Each process runs the following code where I represents each process, which process we are. Weighting n and key and lock are initialized to false, each process is a local boolean code. I think what this is, I don't know why I didn't write it, but. I think this is a solution for multiple processes. Remember we said Peterson is only for 2? And also we said the lock was only for 2, the compare and lock was only for compare and set. No, compare and
Swap.
compare and swap and the other one was called test and set. So those are only for 2 of those solutions. Here's a solution for more than 2. So what do we say here? We say like this, I'm I, right? Notice this, is there J? Oh, there's J. Yeah, but J is the next one. You see? It could be many. Whenever you see like this, I plus 1 percent n. Percent n means we're going to go wrapping around. So if there's 10 solutions, when I'm on 9, it'll be 9 plus 1 will be 10. And then 10 modulo 10 is 0, so I'll back to 0 again. So I'm going through all the processes, assuming that there are 10. Well, however many there are. So what do I say? I say, I am waiting, which means which means I'm interested, right? Waiting equals true. And I say key equals true. And then I say, if waiting and key are true, in other words, if I'm waiting and I have the key, well, I do in this case, because I just set them to be true. So now try to lock. So the first process to execute will set the lock to true. And it'll be locked. But have key set to false. Oh, because you see how key gets the return value of test and set. Remember what test and set is? It changes the value, but gives me back the original value. So if it was open, if the door was open, key will now be false.
It's now locked in.
I've locked it, I've gone in, but I've set the key to false. It will break out of the loop the next time around. In other words, I have the key, and here, so I'm doing this loop, but this loop is not an empty loop. It's got one line in it. And the one line is to attempt to lock. Now, if it comes out that it's already locked, I'm not going to do anything. I'll just keep on being, my key will keep on being true. Because key will be true every time this, if I go in and the lock is true, key will be true. So I'll just stay in my loop forever. But if I'm the first one, then I'll go in and I'll get key to be false. And when I go back to the loop, key will be false. And since my conditions are not both true, I'll break out of the loop. Now I'll say, well, I'm no longer waiting. I'm in the critical section. So I'll say I'm waiting is false. So my key is false and my waiting is false. Everything is false, but I'm in the critical section. The key is local. That's a key point. The key is local. And the waiting I is also local. I mean, it's not local, it's shared, but I'm checking myself. Waiting of I means me. But the key, it's very important, a key point is that the key is local, is not shared. So because otherwise, if I would have set the key to false here, then all the processes would all of a sudden fall in, right? If key, I'm setting it to false, it would be a shared variable. Then everybody's checking key would go in, but it's not shared. And waiting I, well, I'm the only one on waiting I. I'm waiting I, the other guy's waiting on I plus 1 or I plus 2, whatever he is. So I'm going to go in now into my critical section. And then I finish my critical section. And what do I do? This is kind of what you guys are talking about setting the next guy, except we're doing it with test and set. We're not doing it with swap, with with the more complicated one with 3 variables. It's just one thing, test and set. And now we're gonna say let J be the next guy in the line, the next process number. I'm process number 1, so let J be process number 2. Because +1 modulo n, the modulo n is not really that important to us, but basically J is the next guy. But if I'm 2, then J will be 3. Wherever I am, I'm allowing the next guy in basically, and I'm saying like this: if J is not me, as long as J is not equal to I, so it's not me, and J is not waiting, well, if J is not waiting, basically I'm just checking if J is not waiting, and also J is not me. If I'm the only person there, if J would be me, then I'd be the only person there. But let's assume that that's a weird case, and that's the first test. We'll think about that after. First, let's think about what is this waiting? Well, this is saying if J is not waiting, then that means he's not over here. He's somewhere else. He hasn't gotten to this line of code yet. He's maybe in the beginning of the program somewhere else, so who knows where he is. He's not interested in getting into this critical section. So if he's not waiting, then, and he's not me, then pick another J. Because I don't want to let somebody into the loop. I don't want to let somebody into the critical section who is not even waiting for it. Deals with the idea of progress, right? We said that we don't want to let somebody in who's not at all interested in going in, because then that's going to stop the critical section from being accessible to people who really genuinely are interested. So J is not interested in going in. So guess what I do? I say J equals J plus 1. I go to the next J. So now it's 2. So first it was 1, then it's 2, then it's 3. Eventually I find somebody who is in fact interested in going in. Of course, I could go through everybody and say, and nobody's interested, and come back to myself. So now I have to check. If I finish the loop, there's 2 possible reasons why I finished the loop. Either I went through everybody and didn't find anybody who was waiting. So then I've come to myself. If J equals I, then I'm the only person there, then I'll make lock equal to false. I'll make lock equal to false. First come, first serve. Whoever comes, there's nobody interested right now. I'll just say the door is open. Whoever comes first will get it. Because nobody's actually waiting. But if there are people who are waiting, so I am going to let the first one that I found, as I was going numerically through the processes by process number, I'm going to let that one in. The first one that I found. So I say waiting of J, which is the one after me, or 2 after me, or 3 after me. I'm going to make his waiting false. Now, if we go back to the top, if his waiting is false, it's no longer true, then he's not even going to do test and set. He's just going to break out of the loop. And he'll go into the critical section. So the test and set won't even actually be used. In fact, as long as there's always somebody interested in going in, we'll only use the test and set once for the first guy. But from then on, there's always somebody interested, and who's going to be letting him in? The guy who just came out. Who's managing the queue? The processes that are leaving the queue. As each process leaves the queue, he's the one to choose who goes in, and not relying on the test and set method, the test and set operation. He's just choosing him. When he says wait of J equals false at the bottom there, that means I found a J who his waiting is true, and it broke me out of the loop. If the first guy I found, let's say the first guy I found, J equals I plus 1. So 2, or let's say whatever. Let's say I'm 0, J is 1. So he is the first one. So now I go to waiting of J, he's true. So I say, well, what's the opposite of true? False. So it'll break, the loop will break. Immediately, this first loop will break here. If the first guy I found was waiting, then this will break. It won't be equal to me. I'll go here and I'll say his waiting is false. Well, if his waiting is false, he's going to break through. He's going to skip over the test, and go in. So I'm never unlocking the door. It's like the guy who comes out of the bathroom, just lets him in without unlocking he lets him in through the window. He just lets him in. There's 2 doors or something. He lets him in through the back door. There's like if it's like a speakeasy, it's like a speakeasy during Prohibition. You know, whoever goes out has the right to let somebody in, but through a different door, through the exit door. You know, when you go out the exit, you know, before the door slams shut, you can let one person in. But then there's a front door with the bouncer, and then that's the front door. The front door is this test and set, and that's if everybody left the speakeasy, then there's nobody to let me in. So I shut the door, but here I tell the bouncer at the front, false. The lock is open. The first guy can go. The first guy wants to go in.
Only after the one you just let in.
Now, if I was the last one out and I looked around and there's nobody at the back door, then I shut the door and I send a message to the bouncer, let somebody in the front door now. That's what I'm doing over here. Waiting equals false. Sorry, not waiting equals false. Here, lock equals false. Lock equals false is setting this guy up to work again now. Because remember, otherwise we're leaving. My point is like this: that if we always find a new person who's interested in going in, we'll never execute this line. This line only executes when we've gone through everybody and found nobody is waiting. Okay, that's the solution for an unlimited number of processes trying to do the synchronization using the atomic action of test and set. Okay. Previous solutions required complex hardware. I guess this test and set is complex hardware. So there are software tools to deal with if you don't want to build that. If you don't want to rely on that, you know, let's say that you're writing an operating system for a machine and it doesn't have that. So you can't cry to the manufacturer. The manufacturer built it. That's the thing. So you want an operating system that will work even if you don't have that hardware. So we have an idea called we have an idea in the operating system called set. The 2 standard operations modify S. S stands for semaphore. So the wait and the signal. It's originally called P and V because the guy who invented it was Dutch or the guy who wrote about it a lot was Dutch. And P is like test and V is set in Dutch. P I think for proberen in Dutch, I remember. Proberen is what proof. Like, you know, this expression in English, the exception that proves the rule. You know what that really means? It doesn't make any sense the way most people understand it. If it's an exception, then it disproves the rule. Why would you say it proves the rule? It's an exception to the rule, so the rule's not really a rule. Oh no, every rule has an exception, and therefore it's not a rule, it's an exception. That's idiotic. Yeah. Rules are not have exceptions. That tests the rule, that proves the rule. Proberen, that probes, you could almost say in English, that probes the rule. It checks if the rule is really a rule.
How would you use that in a sentence?
There's an exception that tests the rule, that's the expression.
So that's how you would use.
In other words, there's a rule that all students have to come on time, and otherwise they're not admitted. And then one student comes late and he's admitted. You say, well, that's the exception that proves the rule. In other words, it disproves the rule. It tests the rule. It shows the rule is not really a rule. It really disproves the rule. It's like also another expression in English that people get wrong is you say that begs the question. You ever hear that expression?
Yeah.
Yes.
It begs the question. People say, I hear it on the news all the times, you know, and the Palestinians, you know, have never been trusted to keep their peace treaties in the past. And that begs the question, will they trust it this time? That's the way people use it. And the way it begs the question in that sense means invites the question. It presents us with the question. That's what it means. To beg the question is to say something like this. How do you know that every Jew, that Yaakov Avinu wore a kippah? Well, it says Vayetzi Yaakov. And he went out. Now, would Yaakov go out without a kippah? Of course not. So that proves that Yaakov wore a kippah. That is begging the question. That's a joke. That's begging the question. Why is that begging the question?
What's the difference? The usage.
Because I'm not inviting the question. I'm not entertaining the question. I'm begging the question. The question was, does he wear a kippah? And I'm assuming the answer to the question in my answer. I'm assuming the answer. I'm assuming the question is not a question when I gave the answer.
This is a question.
I begged the question. In other words, I illegitimately answered the question by assuming the answer. Now, instead of proving what I was trying to prove, I assumed what I was trying to prove. Whenever you assume what you're trying to prove, then it's not a proof. I assumed what I was trying to prove, right? I was trying to prove that he wore a kippah. Instead of proving that, and I claimed that I was proving it by just assuming it. That was my proof. My proof.
How would you use that phrase though? In that context, correct?
Well, you'd have to use it. When a person would give me that proof, I would say, you're begging the question. You're begging the question. I don't accept what you're saying. You're begging the question. That's begging the question. That's illegitimate.
Totally different.
Yeah, people don't know what they're talking about. It's very irritating when you do know what people are talking about, what words mean, and then you hear them misuse it, it just drives you crazy. So I'm ruining your life. I'll give you a third one. The third one is, these are my favorite quotes. Quote is a verb, not a noun. Quotation is a noun. If you say these are my favorite quotations.
No, quote is used as like short form for quotation.
But it's, look it up in the dictionary.
It's wrong.
Quote.
Here.
I quoted my teacher. I quoted Shakespeare when I said
Quotation.
this quotation. I quoted him. I would like to quote you. Quoting is a verb. A quotation is a noun. So you can't say this is my favorite, these are my favorite 6 favorite quotes. You just say these are my 6 favorite quotations.
Open house, University 2016, they asked the whole crowd there, the proof is in the pudding. What's wrong with that? Why is it not that? What's wrong with that phrase?
That's a good, yeah, what is it?
It's the proof of the pudding is in the eating, or something like that.
Right, that's full expression.
Right, and you're saying like everyone's been using it wrong, and
It's not using wrong, they just don't know the full quote.
That's anatomical.
right, why that has anything to do
What
with
is it?
pudding? The proof is in the pudding, what pudding? Why is the proof in pudding?
Right. Proof, it's really the proof, it's not the proof's in the pudding. The proof is in the tasting of the pudding, right?
Right,
It's also here.
no one knew the answer.
Right, here's another one. Speak of the devil.
And he doth arrive,
What?
and he doth arrive.
Oh, there you go.
Yeah,
It's an anapodoton. It's when the beginning of the phrase
Is used for the whole phrase.
used for the whole phrase.
Anapodoton?
Anapodoton. There's a whole list of them.
Ah,
Yeah.
so that's the one I know.
It's like a jack of all trades,
Right, master of none.
but there's still more.
Yeah.
Is in some cases better than a master of one.
Ah,
The both.
that's very different.
Yeah.
Jack of all trades.
Yeah, because people use it derogatory, but
Right.
it's actually the phrase is
That is
positive.
Okay, back to our subject. That was our how do you say, our interval, our how do you say it? Our that was our relieving of monotonum, and now we'll go back to our subject. Monotony. So P and V are test and or wait, test and send. Less complicated. Can only be accessed via 2 indivisible atomic operators. So what are we saying here? We're saying while send is less than or equal to 0. So we'll wait on S. See, this one is signaling S. The wait on S will wait forever until it's signaled. And then once it's signaled, as long as the signal is equal to 0, let's say, we'll keep on testing. Actually, you know what, let's skip this one.
It just seems like a lot of, it seems like a.
It looks very simple, but I don't want to talk about it. See, when I start talking about English, then I lose track of my.
It's like a producer-consumer block.
Wait. Let's talk about it. All right, but we should do it in this order. Here's the order that I wanted to see it. It's the same way we did with the other one. I'm gonna do it backwards this time. I'm gonna use it first and then explain what it does. So here's the basic idea. I just say wait on S. And then I'm gonna wait here forever. Until finally S is told me that I can go through. In other words, if wait got signaled that he can go through, then I go to my critical section, and now I'll signal to whoever else is waiting on S to go in. So I'm waiting for S until some other process lets me in. And then when I finish, I'll signal that I'm finished and let him in. And again, I'll wait on S. Now the signal will cause me, if I'm the only one there, it'll also cause me to not wait here.
Does that only work with two processes?
No, it'll work, well, it'll probably, right, it probably will have unbounded weight if you have more than two processes. Because we're signaling anybody. We don't know who we're signaling. As long as you're signaling, if you think about it like this, as long as there is no attempt to order the queue, then you'll always have unbounded weight. Here, there's no attempt to bound the queue, to order the queue. In the other example that we saw, the long example that we saw that we did I plus 1, and we kept on checking in a certain order. But here, we're just signaling. Now, what is the internal workings of this weight? So the weight,
Original signal.
what?
It also implies an original signal.
Does seem to imply original signal. Well, the weight is saying like this. First of all, this is the functional description. This is not, it's an atomic operation, but it's not in hardware. This time it's not in hardware. Because that was the whole point. We said we want a software queue. So this time it is in software. And we're actually doing a loop here, an infinite loop here, which we're going to call busy wait, which is not necessarily that good because it means that we're using CPU to loop millions of times a second. And we're checking is S, if it's less than or equal to 0, no, if it's not 1, then keep looping. The minute it's 1, then go in, then the wait will break out of the loop. It'll set S to 0 again, which essentially locks it for somebody else. Right? The minute it becomes 1, he'll go in, because 1 is not less than this. So he'll break the loop, he'll set it to 0, and he'll go in. What makes this operation atomic? If it's not in hardware. The answer is the operating system makes it atomic. The operating system just says, when you call this await command, I'm not going to do an interrupt. So he does this whole thing. And the signal raises it to 1. So the signal raises it to 1, which is gonna, when I'm finished, I remember I brought it down by 1. So I put it to, let's say, 0. Now I raise it back to 1. So you ask, what about the first time? First time's not a problem as long as S is set to 1. If S is set to 1, then I'll do wait to S. S is not less than or equal to 1 to 0. 1 is greater than 0. So I'll go in. So I don't need a signal to start with. It just depends on what S is set as. What if S is set at like 7? So then now we could have actually multiple people going in. What if you wanted a situation like this? That you wanted to allow 7 but no more into the critical section for whatever reason. I have no idea why, but let's say you want 7 to go in. So now couldn't you say set S to be 7, and then 7 is less than 7 is not less than or equal to 0, so that everybody will go in. How many will go in? Well, each one will go in and it'll raise it from 7 to 6 to 5 to 4. Eventually it'll get to be 0, and 0 is equal to 0. So it'll stay in this loop forever. So then you let 7 people in. And then the first one to go out will raise it from 0 to 1, and somebody will go in, and he'll bring it back down to 7. So it's actually very simple. It's actually very simple, but it relies on the operating system to make this thing atomic.
Which part are we doing?
What?
Which part are we making atomic?
Well, maximally the whole weight, but maybe just this, this check and this. See, what the problem is, I'll tell you the problem. What has to be atomic? We can't have a situation where we check it and we found out that it was admissible. We were allowed to go in. And then before we get to decrease it to lock everybody else out, somebody else went in and checked it. Let's say 2 people come and check it and say the door is open. And they both go in, and I was about to lock it, but he came in at the same time as I did. So this and this have to be atomic. You can't, this and this have to be united. So I guess this whole thing has to be atomic. You can't separate the first and last line of that code. So it's a solution, but it's not a great solution because it requires busy wait. That's the real problem. And also, as we said before, it will probably won't work on multiple hardware, on multiple CPUs. Okay. Semaphore usage, so we'll talk more about semaphores. Why did we mention semaphores? Ah, this is called semaphore.
Yeah.
This S, did I mention that here?
That's,
Oh yeah, semaphore S. We mentioned the word semaphore. So semaphore is used to describe a function like this, which precisely has exactly the quality that I just said, that it can be set to 7 or 8. It can be set to a larger number and allow a larger number of people to get in, but at a limit. Only 7, and not more, or only 2. and not more.
What's the semaphore?
A semaphore is a locking mechanism that, well, here we're gonna see, either allows one person in, or multiple people in. A counting semaphore is an integer value can be rate. In other words, when I set my S to 7 or something, then we call it a counting semaphore, because I can allow 7 people into the critical section. When I set my S to 1, then I can only allow 1 in. So it's a binary semaphore. It's a locking mechanism that's binary. And notice it says that when a binary semaphore is actually, if it's binary, then it's a mutex. Because mutex is a special name for a mutual, short for mutual exclusion. Mutex is something that is a mechanism for excluding, is a binary mechanism for excluding. The idea is like this. Instead of writing this whole complicated algorithm to make sure that I am the only one going in and you're not in when I'm in, I have an operating system do it for me. I have the operating system give me something called a mutex. And I just lock the mutex and it'll wait, and I'll just wait at that mutex forever until it's unlocked. In other words, I'll come to the door and I'll say, I don't want to go further unless I can acquire this lock, this mutex. And whoever is the first one to reach that door will acquire the mutex and he'll go in. And nobody else will be able to go in. Now that requires the operating system to give me this facility, give me this resource called a mutex, which is a mutual exclusion device. It could also give me a semaphore, which would be, when I say semaphore, I generally mean a counting semaphore, where it's a mutex that is multiple in size. So then the first 7 people to come to the door will get in. And I would do a function like wait on a semaphore. I would do a wait function on the semaphore. And then the operating system would not let me in or let me in and make me wait. And if it not let me in, then it would make me wait until it could let me in. And if it would be available, it would let me in immediately. And then if I have a binary semaphore or a mutex, then I've solved the critical section problem. I just do, and that's what
Isn't the wait time unbounded?
the wait time, that's okay. Bounded means that people won't go ahead of me. What does it mean for them? But yeah.
Just can't someone go ahead of you? Yeah, I just checked a little bit before you. And then I'm going in, and that means that, I come back again, and I still happen to have checked it just moments before you got it.
Right, so. Yeah, let's have it.
Okay, so we understood this idea of semaphores. Semaphore implementation. The problem with semaphores, as we have seen thus far, is that they rely on busy-wait, also called a spin lock, because it spins, and the CPU is spinning while it's locked. This is wasteful CPU cycles. In other words, this implementation that we see here, in other words, when I'm running this innocent looking command called where is it? Called where is it? Wait on S, it looks like a very innocent little command, but really I'm doing all this stuff here, which is a loop infinitely. Oh, I skipped something. Consider P1 and P2 that require S1 to happen before S2. This is just a use. In other words, I can use this signal waiting idea, not necessarily for a critical section, but for a synchronization. I want that S1 happens and then S2 happens. How can I do that? Simple. I just have S2 do a wait on this variable, which will be set to false. And it will wait there until I signal it, until process one signals it with the sync. In other words, it'll say signal sync, and that will release P2 to continue. So P2 won't do process S2 until S1 has already happened. But anyway, as I said here, this is all wasteful because we're relying on this implementation, which has a busy waiting, which is taking a lot of time. So therefore, spin locks are not so bad when the wait time is expected to be short. Because if we're going to wait for only a few spins of the spin lock, then it's not so bad. And after all, they do save context switching, because if I would go into a real wait, in other words, I would go to, let's say, an IO kind of wait. Like, remember when we wait for IO, what happens? We release the CPU for some other process, which means we do a context switch. So actually, there is a certain advantage to doing a spin, which is that I won't do a context switch. All this time that I'm spinning here, I'm not going to do. I'm keeping the CPU to myself. So if I would do a very short time, then it might be better than the wasting time doing a context switch. So that's just kind of some points to be made here. So what about a semaphore relation with no busy wait? When a process attempts to lock an unavailable semaphore, the process will block itself. It'll just go into blocking state. This action will mark the process as waiting, so the schedule will know that it's not ready and won't bother scheduling it. It'll put it in a queue for the semaphore. The process will be started when another process performs a signal. Then all the people on the queue will get turned on, and they'll be in the ready queue. And the first one to grab the semaphore will go through. Each semaphore can have its own waiting queue. When a signal occurs on a semaphore, the semaphore will restart. It's possible to also do it differently, where you have a semaphore with its own queue, and then when the semaphore is signaled, then only the next process in the queue gets started. Now, a semaphore structure could look like this: semaphore with a value. Remember, we said the value would be like 7, for example, in my case, where we want to allow 7 processes to go in. And what is this process list? This will be a linked list of all the queues of all the processes that are waiting for this particular semaphore, for the one that we set to 7. So we have wait and signal implementations. So this is the actual implementation of how we're going to do this wait. And we're going to say like this. This is a different way of doing it this is an implementation without busy wait. That's the idea. So what do we say here? We say, well, this is the function, wait, and this is the function signal. Okay, and we're obviously waiting on a particular semaphore. So the first thing we do is we say, take the semaphore and lower its value. Now, that could be that the value is 7 and we set it to 6, but it could also be that the value is 0 and we set it to -1, or -1 we set it to -2. We don't know what the value is. So we're just taking whatever the value is and reducing it by 1. And now we're saying if the value is less than 0, well, what does that mean? If it was 0 and now it's less than 0, then we don't want to run this process. I mean, I guess we're assuming here that if it is 0, you see, it's okay. Because if it's 0, then why is it 0? Because it used to be 1. So we reduced it from 1 to 0, so we're allowed to go in. But if it's negative, if it's less than 0, then add this process to the S list, to the list on this semaphore S. Notice S has a value and S has a list. We just said S is a structure. It has a value and a list. So the value we lower and we put it onto the list. And we don't let it go in. And then we say block, which means we ask the operating system to put us off of the ready queue. Don't be on the ready queue. We're not interested in the CPU. So now we have no busy wait. We're in the ready queue. We're not in the ready queue. We're blocked. That's what we did in wait. Now, what if we didn't do it? What if it was like 7? So if it was 7, we reduce it to 6. And is it less than 0? No. So we skip over this and we just keep going on. So this function, the wait function, will take only 1 line. It will only be 1 line of execution in the case that I'm the first one there or the first 7 there. Now, what about signal? Signal, when somebody leaves the semaphore, he wants to let other people in. So what will he do? He'll increase the value by 1. So if it was, let's say, -7, now it'll be -6. And what will he do? Well, if it's -6 now, what does -6 mean? How could it be -6?
Those are 7 things in the cube.
It means that there's, right, 6 or 7, I don't know, you think about it, in the queue, exactly. So if the value is negative, then remove a process P from the list. Because there's somebody on the list that if we just got out and this list is 7 long, then there's gotta be somebody interested in going in, we better let him in. So remove a particular one from the list and wake up P. First, remove him from the list. In other words, take him off the list, delete him from the list, and then wake him up. Wake him up is the opposite of block, which means put him into the ready queue. So the one that we wanted to put in the ready queue, we'll put in the ready queue, and the scheduler will schedule him whenever it's his turn. So we'll put him into the scheduling queue. What if why do we check this? Why do we bother check this? Because let's say the value of the semaphore was 7, and we left, and it's still like 5. So then what does it mean if it's 5? If it's 5?
There's 5 processes there.
No. If the semaphore started at 7 and now it's 5 and we left. So there's like only 1 process there, maybe, or 2. But what does it also mean about the queue?
The queue is empty.
The queue is empty. If it's 5, then we still have plenty of space for more people to come in. So we don't need to bother doing this, remove somebody from the queue, because there is nobody in the queue. The queue being negative indicates, in fact, the magnitude of the queue, and I use the word specifically, the magnitude of the queue tells me the length of the queue. The magnitude of S, the negative if it's a negative number, then the absolute value of that number is how many people are in the queue. So wait and signal must be atomic actions. So this whole thing has to be atomic, which of course the operating system will have to guarantee for us. It's not going to be a hardware solution. The size of the queue of processes waiting for the semaphore is the absolute value of the value when it is negative. Right. There's the size of the queue. The queue may or may not be a FIFO. In other words, we can have the queue as a FIFO or whatever. So you see, this is what I'm saying has no busy wait, right? Because there's no looping here. We're just putting somebody into the ready queue, which the operating system already deals with through interrupts and not through a looping.
The list is managed by the semaphore.
No, the list is managed, well, it's really easier to think about it as it's managed by the operating system. The list is managed by the operating system.
So it's
Well, it's managed by both. In other words,
object.
when I say remove a process from P, well, the method by which I remove that is up to me, it's up to the semaphore. In other words, the implementation of this signal function
Oh, it's
will have a list, and however it removes it from the list is not determined by this particular statement here.
It's by design.
An operating system could write its signal function any way it wants. It could have it as logically, it would be a first come, first serve, perhaps. It could also be not a first come, first serve, it could be random. But let's say it's first come, first serve. To ensure that wait and signal are atomic, we will need to disable context switching during their execution. Well, that's what I've said. This is difficult on multi-core machines, as we discussed. Therefore, spin locks may be required to prevent 2 processes from accessing wait at the same time. In other words, in a multi-core environment. In a multi-core environment, we have to actually have spin locks to prevent the 2 different, because if I have 2 different processes running at the same time, 2 different cores, they could both try to go to wait at the same time. So we may have to lock them one out. When one goes in, you may have to lock the other one out somehow. But you don't have to, not as bad as it sounds, because the operation of wait and signal themselves will be short, so the spin locks will be quicker than spin locking for the entire critical section. In other words, what I'm saying here is like this. This action here is a defined set of actions. And you could say like, well, if I want to do all these set of actions, it's only like 4 actions here. So it's not an infinite number of, or it's not, I know how much it is, it's a defined amount. So if I have to spin lock before and after I do the wait, as if I have to lock everybody out before I do the wait, I know how long I'm going to lock them out. I'm going to lock them out for the amount of time it takes to do these 4 lines. as opposed to doing a spin lock before every critical section, which is indeterminate in how long it is. I don't know what this particular program is. So I don't mind having, if I want to do a lock before I do wait. Right, and I have to lock everybody before I can do the wait, but I know this is gonna be short. So it's not so bad. So even though it will have sort of a reliance on spin locking, but it may. But it'll be short. Okay, now. Deadlock and starvation. Oh, we're just sort of mentioning deadlock here briefly. We're gonna have a whole chapter on it. But deadlock is when two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting processes. So for example, here, notice that it says wait on S and wait on Q. I'm not gonna proceed until I get two semaphores. We can have a situation like that where I need two locks, to launch the nuclear missiles, you need two keys. In order to proceed, this program needs a lock on S and on Q. Now, if the other program needs a lock on Q and S, which is the same two locks, but in reverse order, it could happen that P0 locks S and P1 locks Q, and now they're both in a wait, in a spin lock essentially, well, whatever, waiting. You see, we just got through saying that this actually no spin locking here, but before I do this wait, I'm gonna maybe spin lock. And I'm gonna be stuck here waiting for this guy, and he's gonna be stuck here waiting for me, and we'll be infinite, we'll never release. Of course, the solution would be to have P1 also first get S and then get Q. But that means that we have to have the ordering of the acquisition of the semaphores to be in a certain way. We have a certain order we have to have, we can't just have any old order. We're gonna have starvation, indefinite blocking. A process may never be removed from the semaphore queue on which it is suspended. Why did I write LIFO last in, first out? I don't know why. The queue I don't know.
Someone could always come after. If I'm waiting in the line and then someone comes in now, then he's gonna leave. And then before I get to leave, someone else comes in again.
Ah, right,
You're saying LIFO would be the starvation method.
right.
LIFO would.
Infinite blocking, right. You could also have a leaf, right, if you had a LIFO, then you also would have priority inversion. This is a nice word, priority inversion. Scheduling problem is, what is a priority inversion? Scheduling problem when a lower priority process holds a key needed by a higher priority process. Okay, so I have the key for you, but you're a higher priority. And a middle priority task preempts the lower one because he has a way of preempting him because he's higher than the lower one. But that will cause the higher one to wait even more because he was waiting for the lower one. In other words, if I have a high priority task, which doesn't do preemption for some reason, but a middle one which does preemption on a lower one, then I could end up causing that. In other words, preemption is a tool to be used sparingly because you have to think, well, maybe there's some, if I don't use it across the board, I could cause priority inversions. And if I don't, everybody, grant it to everybody, if I just grant it to one place and not every place, then I have to think about how I'm doing it. How are my priorities working? Do I have my priorities right? But there is a solution called a priority inheritance protocol, which is the priority of the lower priority task, which has the critical section, is increased by inheriting the higher priority of the task which is waiting for the resource. In other words, if I am holding something and you're being polite and waiting for me, then I will get your priority if yours is higher than mine. So that nobody can preempt me if they can't preempt you. In other words, if you're waiting for me, then it must be that I'm a high priority, so I better inherit your priority. Now the middle task cannot preempt this low task because he got the higher priority. This allows the higher priority task to use the critical section as early as possible without going through the preemption. It avoids the unbounded priority inversion. What's the question?
Without seeing the higher priority, how does it know that the lower priority is a higher priority? All it knows is it sees this lower priority process, reads the process, and goes like, oh, there's a resource there. And
No, as soon as the higher, you can do it like this, as soon as the higher priority is waiting for some task, it immediately checks the priority of that task versus itself and assigns the other one its priority. Right, I come along and I'm waiting for you, and your priority is low, so I'll give you a higher priority. I want you to.
So you have to be seen first.
Yeah, you got in there first, obviously, that's why I'm waiting for you. You got in there first, preemption, we don't wanna do preemption. It's kind of like, you know. If I'm waiting in a chow line and the general's behind me. He'll give me his general oak leaves or whatever, so that nobody else, some captain won't get in front of him. So some captain won't get in front of me while I'm waiting. Okay, that's called a priority inheritance protocol. So we're gonna end with these three classic problems of synchronization, which everybody learns in this course, especially the last one that is the most memorable. Bounded buffer, readers, writers, and dining clusters. We talked about readers, writers before, or we talked about bounded buffer before. It's related to readers, writers. So bounded buffer. We talked about this before, but we're just gonna see it a different way now. N is the size of the buffer. How many items can the buffer hold? We have a semaphore, we'll call it mutex because it's gonna be a binary symbol. Initialize with value 0. The semaphore is full. Semaphore full, there's two semaphores, one mutex, which is true, and there's another one full, which is false. In other words, we're not full, but the mutex is locked, but the mutex is available. Semaphore empty, initialized to the value n, or n is the size of the buffer. So empty will tell us how empty it is, and full will tell us how full it is. So empty will start off being, let's say, 10, because it's very empty, and full will start off being 0 because it's empty, it has nothing, not full. A weight for either the full variable or the empty variable will attempt, but not necessarily succeed, to lower the value of the variable. So weight for either of them will lower the variable. Weight lowers. If the variable is already at 0, the weight will cause the process to block. Okay, so weight is going to lower the variable. So let's see. The structure of the producer. The producer says, first thing I do is I produce an item and I'll call it next produced. So I'm just storing it though. I'm not yet putting it into the buffer. It's just by me. And then I say weight empty. Assume, for example, empty is 4, indicating the buffer has 4 empty spaces. So what will weight do? We said weight will lower the value. So weight will change empty to 3. Now mutex attempt to enter critical section lock mutex. So the mutex is started at 1. Initialize the value of 1, which means I can lower it. So my weight will let me lower it. So I'll produce an item, I'll go in, add next produce item to the buffer. So whatever that will be, some kind of command like insert into the buffer this item next produced. Then I will increase the signal. Did I write here what signal does? Well, it doesn't say here, but signal is the inverse of weight. So I'll increase the mutex back to open available again. And I'll increase the full size to that it's fuller. Notice here, I lowered the empty. I didn't raise the empty again because that's not my job. It's not more empty now, it's more full. So I'll raise the full. And then I'll do it again. And I'll keep producing. Now, if I can keep doing this and there's no consumer, then eventually empty will get to have before 3, 2, 1, and then empty will be 0. And I can't go any more empty than that. Notice I can't have nothing to empty out. I have no more space. And full will go up to 4. Now, what is the structure of the consumer? What does the consumer do? He waits for full, because if in the beginning full was 0, then he has nothing to do. He'll wait there forever. As soon as something goes in, he will progress. And he'll say, well, I'm not going to remove anybody unless I can get the mutex. Because the mutex is going to guarantee me atomicity. There's a word like that? Atomicity? Atomicness? That it should be atomic. Atomicity.
You don't need it. Well, you don't need to be atomic, you just need to not be happening at the same time as anyone else.
So that's called atomic. And I need that this action called. I need
non-synchronity.
Fine, exactly. Whatever. It's a critical section. I need to remove the item from the buffer while nobody's putting something in. So I will now get my mutex. Because remember, the full didn't guarantee me anything. The full didn't guarantee me that I'm not going in at the same time as you. I just found out that there's 6 items there. So now I'm going to remove one, but I better remove the right one, and we didn't talk about the right one, but I don't want to interfere with your putting stuff in. So I lower the full, and then I increase the empty. And then we move an item from buffer to next consumed. And then I consume it, fine, I consume it in my own free time over here. And then I go back, so the critical section is removed. If we have several consumers. What do we have several consumers? So this is fine and dandy for two, or one producer, one producer, what do we have several consumers? There'll be a race condition between them for the semaphore. One of the consumers might starve. Same is true of the producers. In other words, if I have multiple consumers here. It could be that it's full, it's 6, and I quickly jump in, lock the mutex, empty it, and jump right back to try to get another one. And I could be somehow I get ahead of another one. So I have a race condition. We don't know if there's no ordering here. There is no organization of the consumption. There could be some kind of prejudice here, that somebody, for some reason, always manages to get ahead of the other guy. So we generally don't like that. We generally want to have predictable results. Okay, that's the bounded buffer problem, and I think I think this is an interesting thing because we're using the idea of this weight on the full. I think the full is really a semaphore. Did we say that? Yeah, semaphore full. We've explained now why we want a semaphore that could be 7. Why would we want a semaphore that's 7? Because that semaphore is going to indicate for us the size of the buffer, and it's not. We're not going to go into the critical section with that semaphore. We're just going to know that the space in the buffer. We're still going to use a binary buffer, a binary semaphore called mutex to determine to create mutual exclusion. Question.
Why do we need empty and full?
Um,
When the semaphore typically have 1 semaphore spaces, as long as they can only be changed using like when you're within the mutex.
well, what do you want? You want, let's say you want just empty.
Yeah, just empty.
Just empty. So he will wait. So the producer will see that empty is available. So he'll empty things out. And then over here, what will we do here? He'll wait on empty. He'll signal empty. What will he do? Empty, we can't both be waiting on empty because if empty
Yeah, I guess
starts
what
out, he's lowered empty. What is he gonna do? He's gonna lower empty.
So now the producer would wait on empty, or
No, he would,
opposite, then the consumer would signal, so they would.
he would have to signal on empty, but why should he signal on empty? He doesn't know anything about empty. What would you have him do? In other words, if we just had empty, for example. So then what would this signal be? This would be nothing, it would be just deleted? Would we get rid of it?
The signal full,
Signal is full, we just get rid of it, or we signal on,
you'd
it
wait.
couldn't be signal on empty, because if it was signal on empty, then we wouldn't have done anything. We would have lowered it to 4, we've lowered it from 4 to 3, and then raised it from 3 to 4.
Then you wait.
So,
So you
but why
switch
wait? We want to be able to produce as much as we can until the buffer is full. So we would just do empty, we would just have empty and have no line here, no signal full. Because we would want to keep on producing as long as there's space. So then let's come over here. All we have is empty. So we have to get rid of this line wait on full. What would we put? We can't put wait on empty. Because we did wait on empty, then if the other guy produced everything, it would go down to 0 and we would try to go in, but it's empty, it's fully empty, but the emptiness would have gone down, which means it's full. But that's not good for us. We want to consume. We want it to. We don't want to wait for that. We want to signal it. So what do you do? Signal here? But we can't signal here now.
Right.
Oh, we would just do nothing here. And we just do here signal on full. We would just go in immediately and remove one. But that would. But then we don't know if there's anything there. We would go in immediately and remove an item, but there's nothing there. And then we would signal that we took one. We'd raise it. But maybe we took nothing.
Right, okay.
It won't work. It won't work any other way. I mean, any other way, probably another way, but you need both of them.
Just feels weird because we so far used what's it called? Forgetting the word.
I understand, because being empty and being full,
Yeah.
being empty and being full is the same thing in reverse, so why do you need both of them?
I've used 7 to say like if there are no lessons that we initialized it to 7, then we know that, you can wait on.
You need both, I don't know, think about it, try to find another solution, go back your shot. You're welcome, to try. So now we're talking about reader's writer's problem. Reader's writer's problem is similar to bounded buffer because we're producer and consumer, except here, what's the producing? The producing is writing and the consuming is reading. What's the difference though? The reading doesn't there's no problem with multiple consumers. If I had multiple consumers in this place, then well, actually, I shouldn't say there's no problem. I said if there's several consumers, there'll be a race condition, because it's hard to know who will get it. But also, consumption has a limit. Because once I've consumed all the variables, if the producer doesn't produce more, I can't consume anymore, and I'm stuck. But reading, I can keep reading forever. I can have 1 million readers, no problem. Right? Writers, I can't have more than one at a time, but readers, I can have 1,000. So it's like the bounded buffer problem, but here the data set is shared among a number of concurrent processes. There is no data consumption, only reading of data. It's not actual consumption, not getting rid of the data. Readers only read the data set. They do not perform any updates. And writers could read, but they basically write. Problem. This is our problem. We want to allow multiple readers to read at the same time. Only one single writer can access the shared data at the same time. We mean like this. Not only can he not be writing when somebody else is writing, he can't be writing when somebody else is reading. Because if he's writing when somebody's reading, then the reader will get screwed up data. If he's in the middle of changing the data and the reader is reading it, he'll get messy data. Only a single writer accesses the data and no readers or writers can access at the same time. Several variations of how the readers, writers are treated all involve priorities. So shared data sets. So we have a data set, obviously is shared what they're reading and writing to. There's a semaphore called read write mutex, which is initialized to 1, which means it's available. There's a semaphore mutex, also 1, and a semaphore read count, which is 0, indicating that no one is reading right now. So here's the structure of the writer process. The goal is to prevent another process from writing while we write. So we simply do a mutex. Wait on the write mutex, or the read write mutex. I write, and then I release it. Very simple. Producer is simple. I don't want anybody, I guarantee myself mutual exclusion. When I do wait on this, I try to reduce it to 0. So if it was 1, I would succeed and I go in. If it was 0, I get stuck and I wait. And then I release it. What about the reader? That's the writer. So the writer won't go in unless he's alone. What about the reader? Now the reader, we want that he also goes in when he's sort of alone. He's alone in the sense that he's not with any other writers, but he could with other readers. So wait on the mutex. I make it increment. I guarantee that I'm the only one going in. And then I say read count equals to read count plus 1. So if I'm the first one, what will read count be?
0, then 1.
It'll be 1. It'll be 1, not 0 then 1. If I'm the first one,
0, then you see.
when I get to this if here, it'll be 1. If I'm not the first one, I'm going to skip this line. And I'm just going to release the mutex and now read, because I can let other people read while I'm reading. So I got into the read, but wait a second, the real coin is the first one. If I'm the first one, I grab the mutex. Which mutex? The read write mutex, which is who was using that?
The producer, right?
The writer was using that. Really, it should be called like the write mutex. The reader now grabs the write mutex, the first one. It's like the first one in prevents the writer from getting in by doing this. And then he releases the mutex. The mutex was just so that the count was atomic. We wanted this count to be atomic. We don't want 2 people coming in at the same time and changing the count incorrectly. So we have this mutex. Notice the mutex is only used by us. So this mutex is just to make this count atomic. So I come in, I up the count here, and it doesn't. And I know that it's not going to get screwed up because I have this mutex. And then I check it. See, I want to up it and check it that it's 1, because it could be that I go in and somebody else goes in and I raise it by 1 and he raises it by 1. Now it's 2, and nobody found that they were the first one because we both went at the same time. Right? If I went in and did read count, and then he went in and did read count, and then we go to this next line of if, and it could be that we're both checking that read count is 2, and it won't be equal to 1, and nobody will grab this mutex and lock out the writer. So we want the first guy's job is to lock out the writer. All other people who are not count equals 1 can simply say, I'm finished changing count and continue reading, because what do they know? They know that somebody else has done the trouble of locking the writer out. Now, I continue on. And I finished my reading. So now I have to lower the count by 1. Because if I don't lower the count, then it'll never get back to 1. I could be the last guy. So I need to find out, am I the last guy? Because it could be that the first guy who went in is not the last guy to go out. The first guy who locked it doesn't mean that he's going to be the one to release it. Who's going to release it? The last one out. So I do read count minus minus. This is the mutex just for the read count. And now I check, is the count equal 0? If it is, I'm the last one out. I better let the writers in, because after all, there's nobody there reading now. So I do signal on the mutex for the writers, it lets the writers in, and I now release the mutex for the count. Now, so this will actually, as soon as a reader goes in, he locks it, all the readers in the world can come in, and even new ones, some can go out, some can come in. We could have 5 coming in, 5 going out, 4 going out, 6 coming in, 5 going, and it could be that there's a constant flow of readers, and all that time as readers are in, who's locked out? The writer. Therefore, we have a situation of kind of unbounded weight for the writer. The writer is just going to be, or what we call this is preference. We call this is called reader's preference, which means that it's once the readers are in, they say the writer, you can say, well, the writer preference also. No, but not, they can't be a chain of writers, because as soon as the writer goes out, he releases the mutex, and now whoever grabs it first goes in, which could be a reader, it could be a writer. So it's not it's no preference to writers for sure.
Doesn't this code have like the same issues with the reason conditions? The plus means it never reach 1 or never reach
No,
2?
because we have this mutex here. That's what I was explaining. This mutex and this mutex here, that serves to make this whole thing atomic.
Fine.
Okay, so that's called the first variation. No reader is kept waiting unless a writer has permission to use the shared, as we just saw. Okay, I don't know why I mentioned it, wait. What did I already do? Notice that A equals 1 is atomic, but A minus minus is not atomic by nature, because it's really just A equals A minus 1, and that's not atomic. So there, theoretically, there could be a context switch between the A minus minus and the assignment operation. What A minus minus might have?
It's what you just said, that the
Yeah.
mutex makes sure that.
Oh, yeah, between these two lines, A plus plus or the A minus minus, I guess it's what I mean. In which case only one decrement will occur. Hence, there is a need to use the wait mutex before the read count. Otherwise, it could happen, right, we said this. Although this algorithm solves the reader's fragment, it could result in a writer waiting indefinitely, as I said. As long as there's a reader, reading, then a new one comes, the writer will be locked out. Therefore, this is called reader preference. Fine. There are 2 other solutions. Second variation, once the writer is ready, it performs the write as soon as possible. We'll need to suspend readers. What I mean by suspend readers, I don't mean to suspend them in the middle of their reading. What I mean is we won't let new readers come in. Once there's a writer, if you think about this idea, once there's a writer waiting, then don't let any new readers come in. And then eventually the readers will finish their jobs and all eventually go out, and then it'll be empty. It's kind of like, imagine a pool where you have men's hours and women's hours. So as soon as the women's time, we could have a situation like this. As soon as the men's time is over, we don't kick the men out. We just don't let any new men in. So eventually the men, how long can you swim? Eventually the men will get out of the pool, and when there's nobody finally there, then we let the women in. And we don't let any new men come as long as there's one woman waiting. So we wouldn't actually have to have women's hours and men's hours. We would just have this system. And as soon as a woman appeared, no new men can go in, and eventually she'll get to be going. Okay. Both may have starvations leading to even more variations. For example, the writer may be locked out by a constant flow of readers. We said that. Okay, here is solution 2. What are we doing as far as time? Not so much time. This is solution 2. This is solution 2. You can look at it at your own time.
You do the race thing.
Yeah, I'm about to get there. This is solution 2 for the readers writers, where we have what I just said, where as soon as there's a reader, as soon as there's a writer interested, then the readers have to not be allowed to go in anymore. Let's go to the third and last example. Let's call the dining philosophers problem. And the idea here is that you have 5 philosophers and they do 3 things. They either think, when they get tired of thinking, they go to sleep, and when they wake up, they're hungry, so they eat. Now, they're sitting in their chairs here, and notice that there are 5 chopsticks, and there are 5 philosophers. Now, in order to eat, if they're all working at different times, if they're all sleeping and eating at different times, then likely it'll be that each one will wake up and be able to get 2 chopsticks and eat. But it could happen that they all wake up exactly at the same time and want to eat at the same time. And each one grabs the chopstick on their right, and nobody can eat. Or each one grabs a chopstick on the left and nobody. Or some other combination. That means that each one got 1 chopstick and nobody got 2. And they're all waiting to get the other one. They're waiting for the other philosopher to put down the chopstick, but he never agrees to because he's waiting. He himself is waiting for a chopstick. So we have what's called a deadlock, where because they all grabbed at the same time, nobody is going to be able to get the supplies they need. And we can think of this as the bowl of rice is like shared data. The chopsticks are like 5 different semaphores, each one trying to grab one. And we say like this, we say, wait for the chopstick and then try to get the adjacent chopstick. If I'm I, try to get I plus 1, that'll be the one on my right. And then when I'm finished, go off. So this won't work. What is the problem with this algorithm? The problem is that if I gets it, then I plus 1 is J, let's say, and he gets his and then tries to get, each one tries to get the one to, each one gets their first one and nobody can get their second. So is it incorrect use of semaphores? We signal the mutex. I don't know why I put this here. The book just put this here. First, we're just saying here that we could theoretically, like, if you signal before you wait, then that's kind of stupid. You're supposed to wait and then signal. And if you wait and then wait again, well, that's also kind of stupid. You can't wait for the same thing twice. So once you've gotten it, you can't try to get it again. You'll wait forever. If you signal and then wait, whatever, these are both wrong. Signaling and then waiting means that you'll always let yourself in. And waiting means you'll always lock yourself out. And another possible problem is omitting the wait. You just forget to wait or forget to signal. Okay, those are all incorrect uses of semaphores. So this is deadlock, as I explained. There's 3 solutions. That one is let only 4 philosophers sit down. Well, that's kind of breaking all the rules of the game. But you could just say don't let more than, if you have 5 chairs, only use 4 of them. So then if there's only 4 philosophers there. If everyone grabs 1, there'll still be 1 left over. For sure, somebody will get it. That's one solution. But let's try to have it where we have all 5 there. So one idea is only take chopsticks if 2 are available. How, in other words, check that there's 2, and if there's 2, then take them both. Somehow lock 2 at once, or don't lock any. That would also work. But the third possibility is, or an odd numbered, this is the best one, I think, it's the simplest. Odd numbered philosopher takes left then right, even takes right then left. Which means, we go back to the picture, right? Means that then if we call this guy 1, 2, 3, 4, 5, if we say he takes, what did I say? Odd takes, doesn't really matter, but
Odd takes left, then right, even this right.
odd takes left. So he's odd, he takes this guy. He's odd, he takes this guy. He's even, he also takes this guy. So already you see that this guy, 4, is not going to get anything. If 5 went before 4, then 4 won't get anything because he has to take left first. That's like right first. And he can't take this one. So he won't get anything. Well, if 4 didn't get anything, it's kind of like he's not sitting there. And therefore there's somebody's gonna have an extra chop. If as long as we can keep 4 from getting anything, then there'll be 1 extra and somebody will get it. And when somebody gets it, that breaks our deadlock. Because somebody will get it, he'll eat and he'll fall asleep now, or he'll think and he'll stop eating. So that already breaks it. Because, right, because he's trying to get this, but he already got it. And if he got it first, well, then he's gonna be waiting. He just has to get this one first. So if he got it first, then once you have competition on the same one, you break the deadlock. The problem was that they all succeeded on their first thing and couldn't succeed on the second thing. So by doing this odd even thing, we prevent, we make the conflict occur on the first one. And therefore, if you succeed on the first one, you know somebody will succeed in the second. So we lock somebody. So that's the solution called odd number philosopher takes left in there. Now, what about the solution only take shots if you have 2 available? Well, that's with the monitors. Basically, it's making Q. We don't have time to go over it today. But here's the solution. Here's the solution. Actually, here's the solution using not taking 2, not taking unless you have 2. Maybe we'll go over it in the lab. Stop recording.